Hello students, in today's lecture we'll continue with the Routh criteria. Now for Routh criteria, let's take an example, the one which we did in the previous class. Now suppose we have a polynomial equation, that is PS, something like S4 plus S cube plus 2S square plus 2s plus 5. Okay, before we solve this polynomial equation, let's revise first about Routh criteria, what it is, what it was in the previous lecture, what we did before we solve this specific case. For that, let's take another polynomial equation. In order to revise what was Routh criteria, I'm solving another equation, that is, let's say another polynomial equation, that is s6 plus 4s5 plus 11s4 plus 53s cube plus 102s square plus 150s plus 100. Now prepare a Routh, the question is prepare a Routh array for this and check for the stability. Now for Routh array, number one, all the powers of s should be there, that is there. Now we'll prepare an array. Now in this array the number of rows will be equal to n plus 1, where n is the highest power of s. Now the highest power of s is 6, so that means the number of rows should be 7. So 1 2 3 4 5 6 and 7, all the 7 arrays should be prepared, then we can decide the stability. Number 2, we'll start with the first row. In the first row the entry should start from this, the coefficient of this, the alternative coefficients should be written, so that is 1 11 102 and 100. The leftover goes into the second rows, that is 4 53 150. Row number 3, b1, and what is b1? b1 is equal to 4 into 11 minus 53 into 1 divided by 4, that is b1. So this comes out to be minus 2.25. b2, that is 4 into 102 minus 150 into 1 divided by 4, whatever that calculation is. So b2 comes out to be 64.5. and then b3, that is again 4 into 100 minus 1 into, if there is nothing we take it as 0, so 1 into 0 0, 400 divided by 4, 100. Then next row, c1 is again this into this minus this into this divided by this sign. So what does c1 become? c1 becomes, over here c1 comes out to be 167.67. c2 minus 2.5 into 150 minus 4 into 100 divided by minus 2.25. So this comes out to be 327.78. 5, this into this minus this into this, so this becomes 68.9. and then we have this 167 into 100 divided by 160, again 100, and then the next one 84.43, and then the next one 100. Clear? Now since all the array has been prepared, now what is to be done for stability? We're going to need to check the sign of the first entries in the first column. So for stability, remember this, for a system to be stable, all the elements in the first row of an array should be positive. Now 1 is positive, 4 is positive, we have a minus sign, positive, 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 positive. So only one row, this row is having a negative sign. That means the system is unstable. That means the system is unstable because we have one negative sign. So that means there, okay, now the system is unstable. Why it is unstable? We'll now look at the number of roots that make it unstable. For that, look at the sign change. Look at the sign change. Positive to positive, positive to negative, one sign change, negative to positive, two sign change. So there are two sign changes, which that means there are two roots which make the system unstable. That means on the imaginary axis there are two roots, they are lying on this side of the complex plane. Rest of the roots, rest all the four roots of this equation, rest all the four roots of this equation are lying on this side, which is making it stable, because we know that this region is a stable region and this region is the unstable part. So all the four roots of this equation are lying on this side, whereas there are two roots which are lying on the other side, which makes it unstable. Clear? So this is how your Routh criteria works. Now let's take another example which I have written over here. Let's take this example. Now let's prepare the Routh array for this. Again, the highest power is 4, so we're gonna prepare a Routh array with 5 rows. So we start 1, 2, 5, 1 and 2. Then in the very first entry it becomes 0. Now when we have a 0 over here, we cannot proceed further. Once we cannot proceed further, we cannot determine the stability of this system. So the array has to be prepared for this thing. Now since we have 0 over here, we cannot proceed further. So how to solve this thing? So this is your basically your special case number 1, when any row first element is 0. When in any row the first element is 0. Now for this there are 3 different ways to solve. First, you can adopt any method to solve this thing. The result will always come out to be the same. So that's why you can refer to any method. So the first method is epsilon method. First method is epsilon method. What we do is we replace 0 by a small positive epsilon number. Remember, the small positive epsilon number, and prepare the array. So let's prepare the array. So this becomes 2 epsilon minus 5 over epsilon, right? And this becomes 5. So that means the array is full. Clear? Now look at the positive sign. Now let's look at the sign. Let's look at the sign convention in this row, because for stability we have to see the positive. We have to see that all the elements should be positive. Positive, positive. 5 is positive. I've said this is a small positive number. This is positive. Now this is doubtful. This entry is doubtful. That is 2 epsilon minus 5 over epsilon, or we can write it as 2 minus 5 by epsilon. Clear? Now in this, what we're going to do is we put limit epsilon tends to 0. When epsilon approaches 0, this term becomes negative. So 2 minus 5 by epsilon, if epsilon is a very small number, so 5 divided by any small number will become greater than 2. So 2 minus something greater than 2 will be a negative. So that means this term, this entry is negative. Now in first row, if any entry is negative, the system is unstable. So this is how you decide by epsilon method. Clear? Now this is one way. Now in the second method, Second method is, what we do is, second method is S plus A method. In this, what we do is, we multiply our polynomial equation by S plus A, where we take the value of A to be a very small value. Let's say we take A equal to 1. So we multiply our polynomial equation by S plus 1. So that is S plus 1 into our polynomial equation, that is S4 S cube 2S square plus 2S plus 1. We multiply our polynomial equation by this. So what do we have is S5 2S4 plus 3S cube plus 4S square plus 7S plus 5. Clear? Now we have this new polynomial equation. We'll prepare an array for this. Again, now the highest power is 5, so number of rows should be 6. So that means 1, 2, 3, 4, 5 and 6. We'll prepare an array for this. So the array will be like 1, 3, 7, 2, 4, 5. Prepare an array, so it comes out to be 1, 4.5, minus 5, 5, 5.5, 0 and 5. Now look at the entries in the first column. All entries in the first column. So there is one negative sign. The system is again unstable. So whether you go by second method or you go by the first method, the results remain the same. It remains unstable. Then comes the third method. Third method, where what we do is we substitute S equal to 1 by x in the polynomial equation. We substitute S equal to 1 by x in the polynomial equation. So our polynomial equation, that is PS, when we substitute S equal to 1 by x, becomes 5x4 2x cube 2x square plus x plus 1 equal to 0. It becomes this thing when we substitute S equal to 1. Now we prepare an array. Again, the highest power is 4, so number of rows should be 5. 4 and 5. So number of rows should be 5. So let's prepare the array for this. So it is 5, 2, 1, 2, 1, minus 0.5, 1, 5 and 1. Now again look at the sign in the very first entry. There is one negative sign. So that means the system is again unstable. So whether we go by the third method, whether we go by the second method or go by the first method, the results remain the same. That means a system whose polynomial equation is given by this polynomial equation is always unstable. So you can approach by any method for this type of special case where the first element in any row is 0. So that's your special case. Clear? Then comes, we have another special case, which is where all the elements in any row is 0. So let's have the another special case where all the elements in any row are zeros. This was the case where the first element was 0. Now we have a case where all the rows are zeros. Like for example, let's take an example. Suppose we have a polynomial equation S4 plus 9s cube plus 4s square minus 36 minus 36s minus 32. Now let's prepare an array for this. Now the elements are the highest power is 4, so number of rows should be 5. So let's prepare the array. So 1, 4, minus 32, 9, minus 36, 8, minus 32. We have 0, 0 and 0. Now so this is that special case where the fourth row is having all the entries as 0. Now how to solve for this? For this type of case, what we do is we will first prepare an auxiliary equation. An auxiliary equation. Now what is an auxiliary equation? Auxiliary equation is an even order equation which is prepared from the row which is previous to that of the row where zeros entries are there. I again repeat, auxiliary equation will prepare an auxiliary equation from the entries where we have zeros, the previous row which is having zeros. Now suppose in the fourth row we have zeros. Clear? So auxiliary equation will be prepared from the entries which are just previous to this. That means we're gonna prepare the auxiliary equation using these elements. Clear? Now suppose if number of zeros are coming in the sixth row, then the auxiliary equation will be prepared from the fifth row. Clear? So from the previous elements, previous row will prepare the auxiliary equation. Now we set the auxiliary equation to be even order. So how we determine the even order? So that means it can be S4, this can be S6, this can be S square, this can be S8. So depending upon the number of elements there, Now the last element which is there, that is over here, is minus 32, will be the constant. Remember this, the last element which is appearing over here is minus 32, it becomes the constant of the auxiliary equation. So the auxiliary equation is minus 32, then the second entry is 8, so it becomes 8s square. We said it's an even order equation, so even order is S2, S4, S6 and constant. So the last element is a constant, and then the leftover element will become the coefficient of s square. So 8s square minus 32 is our auxiliary equation. Let's say it is A. Clear? Now we have the auxiliary equation which is 8s square minus 32. We'll take the derivative of this auxiliary equation, so it becomes equal to 0. So auxiliary equation is this, so this can also be written as s square minus 4 equal to 0. We'll take the derivative, so it becomes 2s, simple 2s. Clear? Now we're gonna replace the zeros by the coefficient of this equation. Clear? So now once after taking the derivative of the auxiliary equation, we'll replace the zeros by the coefficient of this derivative equation. So now our array becomes, so now these zeros will be replaced by the coefficient of this equation. So coefficient is 2, so we're gonna write 2 over here, rest entry will be 0, and we'll prepare an array. So 2 goes over here, so it minus 32. So the array is prepared. Clear? Now we look at the sign change. Look at the sign change: positive, 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 negative. So the system becomes unstable. Since there is one sign change, so there must be one root which is lying on the positive side of the imaginary axis. Clear? So this is how we solve for a special case. Now let's take another example. Now suppose I have a polynomial equation which is something like s7 5s6 plus 9s5 plus 9s4 plus 4s cube plus 20s square plus 36s plus 32. Now let's prepare let's find out the stability of this equation. We'll prepare an array 7, so we have number of rows to be 8. So 1 2 3 4 5 6 7 and 8. Until unless the entire array is prepared, we cannot comment upon the stability. So that's the main part of this. So let's prepare 1 9 4 36 5 9 20 36. So this becomes your 36 by 5, this becomes 0, this becomes 44 point, 5, then further 9, 0, 36, 0 and 0. Now we have the fifth row with all zeros, so case number 2. So now what we do is we prepare an auxiliary equation from the entries in this, from the fourth row. Now auxiliary equation, we said the last entry will be constant, so 36 plus this 0, so this is 0s square, this is 9 plus 9s4. So that's our auxiliary equation. So auxiliary equation is basically 9s4 plus 36 is equal to 0. So this can also be written in other way as s square plus 4 equal to 0. Derivative ds by d equal to 2s. So we replace all the zeros by the coefficient of this. So it becomes 2. There's nothing, so rest is 0. Now again we prepare an array. We again prepare an array. So sorry, my fault, it's my mistake. I've done something wrong over here. Yes, if we take the this is s4, so if we take the derivative, this becomes 4s cube, so it has to be 4 over here, not 2, right? 4. Now we again prepare an array. 4 zeros are 0 and 36. So now the first element is 0, so you can use that. Now it becomes this special case number 1. You can use any method. So let's use the first method. We'll replace it by epsilon. I prefer, if you ask me, I prefer to go by method number 1 because that's very easy. So we have epsilon, proceed further, so it becomes minus 4 into 36 by epsilon, and it becomes 36. Now the array is prepared. Now look at the sign over here. Positive, 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 positive. 36 is positive, epsilon is positive, but this element is negative. So the system is unstable. Clear? So this is how you determine the stability of any system using Routh criteria. But there are drawbacks for this. Now let's look at the drawbacks of Routh criteria. Now if you look at the drawbacks, can you determine the drawbacks? Number 1, the drawback is it only tells us about the stability of the system. It only tells us about the stability of this. It doesn't tell us about the exact location of the roots. It do not tell us about the exact location. Okay, it tells us yes, the roots are stable, they are lying over here. It tells us the roots are unstable, they are lying over here, but doesn't tell us the exact location where the roots are. So that's the number 1 drawback. Second drawback is it only solves the stability for polynomial equations. Now suppose if in the system, if we have something like, we have an exponential term over here, e minus s, a lag term, then it won't tell us about the stability of the system. So that's the only drawback. It only determines the stability of the polynomial equations. For lags, for dead times, for transportation lags, the system fails. The Routh criteria fails. Number 2, it tells us only about the stability. Yes, the system is stable. Yes, the system is unstable. It do not tell us exact location where the roots are from the imaginary axis. Clear? So that's it with the Routh stability. I hope the topic appears to be simple to you. Try as many questions as possible. We can discuss later on for the numericals. Thank you very much.